Okay, this is problem 737. This is another transverse shear problem with built-up section. So here this I-beam that's formed of three elements, these two T sections, and then they're bolted together with two plates here in the middle. Okay, they give you the there's shear. We're just going to consider shear. It gives you the bolt spacing. Two bolts here at each section, and they are through bolts, and then the max shear force in a bolt is 15 kips. Okay, so that's the max shear force in the bolt. Okay, what they want you to find is the maximum V that can be applied onto this beam. At what point will this V become so great that it causes the bolts to fail? Okay? All right. So again, on this one, the force, okay. This is obviously going to be a transverse shear problem. All right. The location that we're interested in here is right at this point. Okay, this line here. This is the line where the bolts are going through, right? So I'm going to kind of draw the center line through here. So that's the plane, right? If you look at this top section, I guess these are always a little trickier to visualize. Or I guess maybe it always seems a little less believable that we actually use the transverse shear flow from the VQ on I to get the force in the bolts when the bolts are on a plane that's perpendicular to the, this actual shearing plane, okay? But what you have to imagine is, again, let me look at the end. So here's the top and bottom flanges of the I-beam, and then here's that section where the bolts are, right? Okay. Now, if you imagine for a second that this thing is bolted together in such a manner that there really is no slip, okay? In fact, as this bends, the whole section has to bend as we've assumed I-beams or these sort of sections bend. So what I'm saying is this differential section has to all bend just as we've imagined beam bending in the past. So all the planar sections remain perpendicular to the deformed neutral axis, and they also are parallel. Okay? So we have to now make the assumption that there's no slip in the plates, no slip in the bolting. So the whole thing deforms like this. Okay? So this is kind of the assumption. This is a deformation that's consistent with Euler-Bernoulli beam theory. So I guess I should write Euler-Bernoulli. Right? Depends upon which elastician you like better, Euler or Bernoulli. Okay, so if that's the case, then if I just look at this top T section, just draw that top T section. Now, of course, I'm obviously exaggerating the deformation, right? Because we have a V, right? Because we have the V down this way, the argument for the V comes about that we have, and here's the neutral axis, right? Let me draw the neutral axis. So if we extend this down, what basically happens is this is in tension, it goes to here. Let's assume this is in a lesser tension. Right? So if you look at the force distribution on this right side, versus the force distribution on the left side. Correct? On this point, we have some M, and then we have an M that's a little greater, right? That's what gives us the V, right? Because the V, remember, is the derivative of M with respect to X, right? This is delta X. All right, so this Q is what gives me the V. That's what gives me the whole, that was the whole argument we did the derivation of what is the transverse shear stress, right? That's where we got the transverse shear stress equation. Because when you look at this, right, the net force on this side is greater than the net force going this way. So that means there has to be another force that balances that out. This is the shear force, the Q times the length times d x, if you will, right? Right? And that has to equilibrate that. So if you look at this top section, this T section, excuse me for being long-winded on this, but sometimes this is seems a bit mysterious, and I can understand why. I actually remember when I was an undergraduate why this seemed a bit odd as well. All right, here I've just drawn the top section. So there's this net force that has to be applied on here, this Q delta X, okay? Where's that going to happen? Well, normally if this were one contiguous beam, it would be happening on this section, but it's not. The only place that's being picked up is at the bolts. So that means we're going to get half of it on this side and half of it on the other side, right? Because that's where the bolt goes through on both sides, all right? So this is going to basically be the 1/2 Q delta X and 1/2 Q delta X. This is again the Q. This is the Q we get from the VQ on I, right? The shear flow Q. Okay, now that being said, in this case, delta X is going to be the bolt spacing, right? So we're worried about this. This actually is going to be S. So the shear force in each bolt is going to be 1/2 of that Q, okay? The bolt is going to be a double shear. So if I look at the bolt, here's a bolt, exaggerating it a little bit. So basically, you've got double shear bolt going on where this is going to be the QS on 2, QS on 2, and this will be QS, right? It's the double shear. So if we look at the shear diagram, give or take a sign convention, it basically would look like this. Where this is QS on 2, minus QS on 2, and this is a positive QS on 2. It might be flipped sideways, but basically it's in double shear. So the shear force in the bolt, the V, this is the V in the bolt, right? Is this QS on 2, okay? All right, so now that we got that, that's kind of the conceptually difficult part. Once you buy into that, and you realize that, okay, it actually is that transverse shear stress, the VQ and I, that these two bolts have to pick, well, this bolt has to pick up. It picks it up in double shear, right? So that the shear is actually half of that, right? So it's half of the QS on 2. Now we can get the force in the bolt, right? This is actually that's the shear force in the bolt. Okay? All right. That's the difficult part. The rest of it is just plug and chug type of stuff. Okay? I need to compute I for the whole section. That's going to be a pain in the neck. I need to compute Q. The V. So okay, well let's get the design equations going. I know I'm doing this a little bit out of order the way I normally do this stuff, but this is the V max in the bolt. So this is V bolt max, right? So we know that has to equal 15. Now I know the Q shear flow is the VQ on I. So now I have VQ on I times S over 2, just substituting in for Q, has to equal the allowable shear force in the bolt. Now we can rearrange this and get V. So that's going to be the max V that we can apply. That's going to be 2 times the allowable bolt shear force times the total I of the beam over Q, which is actually going to be this Q, actually technically just down to this point here. This is the area we're going to use for Q, divided by S. So that's really it. All right. Now let's do the numbers. Okay. Okay. So well, I took a little pause there. Actually, this is the next day, so that was a big pause. But basically, what I need to do now, as I mentioned before, compute the geometric factors, the I and the Q. We already know the Vmax for the bolt. We know the spacing and all this other stuff. So we can do that, plug it back into the equation we derived, and get the Vmax. Okay, so to do that, let me show you. Well, I'm feeling a little lazy today, so I'm going to look at using Mathematica to kind of help automate this stuff. I've done most of these things by hand, but let's look at how you can kind of simplify this stuff using Mathematica. I'm a big fan of these things. So here we're going to, well, here you can do nice things like bring in the pictures and write up text and all that sort of stuff. So I put a little bit in here. The first thing I want to do, or the one that I want to really take the drudgery out of the hand calc, is doing the determination of the geometric factors, the I's and the Q's. So I kind of have that here. And this one's kind of a complex shape. You got two side plates, and then you got a T, and you can imagine the T actually has two plates. So in effect, you have like 1, 2, 3 sections at least that you have to analyze. So let's kind of automate this a little bit. So I'm going to break it up into the side plate, and then the web of the T, and then the top flange of the T. And I'm going to compute the I for each one of those, and then the Q for each one of those. And then we'll add those together and get the I and the Q for the section, okay? So here I already did the side plate. So you can see I kind of put in a base and a height. So the base is 1/2. It doesn't really show it here, but I'm going to assume it's 1/2. And then the height is the 6 inches. So the area is just base times height. Then the I of the side plate is just 1/12 base times height cubed. I can reuse that equation. So I want to store that, so it's I of the side. SP stands for side plate. I don't need to use parallel axis on that. Then we're going to compute the Q stuff. So first we want to get the area for a Q. Well, the area for Q is really just this upper half. So that's 1/2 the total area. Then the distance from the neutral axis to the centroid of that area is h on 2. Actually, it should be h on 4. See, this is what's nice about it. You can correct those mistakes real easy. This is h on 2. The distance from the neutral axis to here is really h on 4. And then you can go through, and then you can get the Q for the side plate, which is the area, the Q area, times that centroidal distance. And there are the values, okay? Now we can do the same thing for the T section, the web of the T. So I'm just talking about this part of the T. So I can actually cut a lot of this stuff. Cut and paste. This won't be the side plate. Now we're looking at the web.
It's okay to write over base and height. I mean, that's really not changing. The base is still a ½ inch, but the height now is 3. The eye of the web is still the same. Now the area, the Q area in this case, is actually the total area. And the location to the centroid is 1 inch plus half of this distance, which is not h on 4 anymore, but it's 1 inch plus h on 2. Okay? And this gets the Q of the web. Actually, I kind of screwed up here. You can see this is the nice thing I can go about it. We need to get the Q right at this point, right along this line, the bolt line. So actually, the Q for the side plate is going to be a lot smaller. The Q for the side plate. Let's fix this. Actually, the area we're going to use is not the area out of half. It's actually this little chunk area. It's not that much really. So it's 3 inches up to here minus the 1 inch well, actually, I'm sorry. I'm taking it back. What am I doing? I don't really use the Q. Remember, I already had this argument here. I'm sorry. That's what happens when I start the next day. The Q I'm only going to use is actually the Q of the T. As for the reason I explained earlier, that this is the this argument up here, right? So the Q I really need is just the T. So the Q for this side plate, well, actually, the area is basically going to be 0. We're not considering it at all. Okay, so I can do that and I get 0 there. Now for the T, we're going to consider the Q is really the Q of the whole of the T section. So we have to do the web. So there's that. That's correct. And we need to do the whole web actually. So I should use the area. We want to get the Q of this whole section. So the area here should be the total area. And this is the YC. So that's right. So that's correct. Now we do this. Whoops. Let's just get this. Let's fix this. Now let's do I don't need this anymore. Let's get the flange of the T section. Let's make it text. We'll use the same equations here. We'll edit them though. So we're not doing, this is going to be the Q of the flange and the I of the flange now. All right, so the base in this case is of the flange is 3 inches. The height is a ½ of an inch, right? You can even collapse these things down. I forget how to do that. I think you can. Well, I forget how you do it. So that's the base and the height. The area is still the same. This is the eye of the flange. That's correct. The area we're going to use for Q is the total area. Now the distance to the centroid is going to be 1 inch, 4 inches, plus a quarter. So it's 4.25. 4.25. All right. And these are the values. Now, I kind of screwed up again. Well, I didn't screw up too bad, but I need to do parallel axis here, right? So I need to get the T section and, both the web and the flange, the eyes have to be pushed by parallel axis. So this is the eye about its centroid. Let's add the parallel axis term. So that's going to be the area times the distance to its centroid squared. So actually, if I put this term up here, I can use that. This is going to be the YC squared. Whoops. Right, so that does the parallel axis shift. We can do the same down here, because the flange also has to be shifted by parallel axis, but we have to make sure we get the right centroidal distance, okay? Actually, I should probably rearrange these. Put all the inputty stuff up first, and then the automated calculations go afterwards. That's always kind of like a decent way to consider doing it. Do that for all of them and save it. But that's fine, just because these first three values are the ones you're really going to want to input, right? The next ones are the calculations. Okay, so let's go through and reevaluate this. Shift enter, shift enter, shift enter. So the Q's won't change. Those I got correct, but you can see actually I got the parallel axis working on here. And the nice thing about the spreadsheet is that when you see you make a mistake, you can go back and fix it real quick, and not have to go through and check all your numbers again. All right, so now we have the I's and the Q's. So the I. So let's now compute I and Q for the whole section. Okay. So I, we have to call it like I total because I is a reserved character in Mathematica. I is going to be 2 times the I of the side plate, because we have 2 of those, plus 2 times the I, well, actually, if you want to get real cute, I can put in here, I could do I of the T is going to be I of the web plus I of the flange. That's the I of one of the T's. And then I could do Q of the T is going to be the Q of the web plus the Q of the flange, right? So that's the T. I'm sorry, why do I have T? It should be I. That's the I of the T, 1T section. That's the Q of 1T section. So I could just do here, the I is the I of the T, right? And then the Q total is going to be, well, basically just Q of one of the T sections, right? It's just one T section. We're just considering the top, right? Remember from the argument we did up here. That's the Q we want, okay? And actually, this is a problem when I take these pauses, I forget. But really I want to get this is the Q of this whole section, right? This is what offloads the differential force through the bolts, through the transverse shear, right? So we want to use that entire section. All right, so now I have the I for the total section and Q for the total section. All right, so that just does all the geometry stuff. And you can see, like, when I make mistakes, which I often do, they're pretty easy to fix here, okay? It just takes a little getting used to the environment. Just like doing problems by hand takes a little getting used to, but also doing problems with Mathematica, once you get comfortable with it, I think you can find that it's easier. All right, so now we need to solve the problem. So now we can solve the problem. We can use this equation. Let's put in some variables. We know that, well, actually, if you want to, we can even put the problem parameters up here. Problem. Let's give that a bolder sort of section. That looks good. And so the problem parameters we have to deal with here are going to be the bolt spacing. That's 8. The V of the bolt, that's the V max of the bolt. That's 15,000. Let's keep it all in pounds so I don't have to deal with units. Also, I think that's it, right? Yeah, that's it. So now I can, oops, what's going on here? Now we can solve the problem. solve for V. Okay, so we're going to use V equals, we'll use this equation, the one we derived just now. So that's going to be 2 times V of the bolt times the I total over the Q total over the bolt spacing. That's the S, okay? And then when I do that, that's the answer in PSI, okay? So now that's the answer. The answer is going to be the max force that you can hold here is 35,000 pounds, 35 kips, okay? I'll probably just write down what I get for the I and the Q. So for this one, well, I'll do that in a second, okay? So that's basically the problem. So that's kind of a nice aspect of mathematics, as it lets you, especially since you haven't had your coffee in the morning. When you go down and you start making mistakes in hand calculation, you kind of have to go back and erase and recalculate, but Mathematica kind of automates all that stuff for you. So I'm a big fan of it. Okay, thanks.